Um, So yeah, thank you for that lovely introduction. So I have worked a bit in, as you mentioned, in delayed feedback and climate modeling. And when I moved to do my postdoc at CSIRO a few years back, I basically wanted to take those ideas that I learned in, from working with delayed systems, bifurcation analysis, dynamical systems, and then try to apply that to kind of the bigger climate problem we have, right? So if we're just thinking about, conceptually modeling some processes in the climate, we can make these nice one-dimensional, two-dimensional, three-dimensional models and discuss the behavior. But how does that translate to this kind of larger world where we have hundreds of thousands of free variables and parameters that we need to be working with? So what I'm going to do today is just give a bit of an overview of the types of problems I looked at during my postdoc with Terry O'Kane at CSIRO, working in what was then called Oceans and Atmosphere, but now we are called the CSIRO Environment. And then also some of the work involved colleagues, Vasily Kitsios and Dylan Harries in the data-driven methods space. So I'll just give an outline first. So I'm going to split this talk up into two parts, basically. And the idea is to show that actually, this is not a one-way process, right? It's not that, theory definitely informs data or data definitely informs theory. That they kind of go hand in hand, right? You can look one way, you can use the theory to inform your data-driven methods and get a better, maybe to improve how you're how you're going about your data-driven methods, but then you can also use your data-driven methods to then peel back your system and understand the dynamics on a lower dimensional space when maybe that lower dimensional space is not so clear from the outset. So we'll just start with get started with part one. So I guess the motivation here had to do with the fact that typically we are working, when we're talking about climate modeling, we are really looking at a coupled atmosphere, ocean, and cryosphere, right? So ice system. And if you think about that coupled system, it's chaotic and it's multi-scale, right? Multi-scale spatially, multi-scale temporally. And yes, we are very aware that there's a lot of chaotic behavior in all of these different subsystems, as well as the whole thing coupled together. Now, typical methods nowadays to estimate the Earth's general conditions from day to day, so we use these for predictions, but also just for pseudo observations, I guess. The methods that are used are data assimilation methods, typically, right? So the idea is that you have a model of the Earth's dynamics, and you have some set of observations of Earth's conditions, and you're trying to get an overall picture of everywhere around the world. How are the Earth's conditions changing, right? And how are they? How does the model move through time, right? So now there's this thing called strongly coupled data assimilation, right, which has been less explored, but is getting more explored in recent years. And that's where you use cross covariances, so across these different subsystems to adjust your unobserved variables and subsystems. So say, if you want to, model your atmosphere, ocean, cryosphere system, you're going to say that actually the ocean can respond to the atmosphere. You're going to take atmospheric observations to inform how your ocean behaves and vice versa, right? And now the other big problem that we have is, well, maybe not problem, but what we know is that the general circulation models and all your Earth system models are of extremely high state space, right? As I said earlier, 10 to the 6, 10 to the 7 variables. That might even be a low estimate nowadays. If you go to real fine, real fine scales, then it might be even more than that. So then essentially we need to perform DA in a reduced space. There's no question about this. You can't just do full data analysis in that full space of variables, right? So the challenges that come along with this, as I've already touched on, are very large spatial and temporal scale separations. We have varying coupling strengths between systems, and sometimes they're unknown. And we have that our observations can often be incomplete. So maybe we only have ocean observations, or we only have atmosphere observations, and they contain many errors. And we also have that your ensemble size is often too small, right? It's much smaller than our free variable space. And so your covariances are not properly sampled often. And so the question that we asked was, can we actually use dynamical properties of a system to inform our data assimilation somehow? right? So just a background, if you're not familiar with ensemble data assimilation, this is a general, nice schematic that Vasily made years ago that gives an idea of what happens. So here you can think that we have an ensemble of only 4 Earths. That's pretty small, but we have basically 4 possible conditions that the Earth was in at a given time to start. And you can take, you take your ensemble average is the average of those 4. And then what you do is you take your model equations and you propagate that forward from T0 to T1. And so your Earths will evolve accordingly to the dynamics. And then you look at an observation from the real world at T1. And then what you do is you pull all of your analysis members or your ensemble members closer to that observation. Right? So then you can see everything's kind of being pulled a bit closer to those gold bits, and then you keep stepping forward and you do this as many times as you like to go forward in time. And what we're doing basically is we know that the spread of our ensemble will widen basically as we push forward. And if that gets too wide, then we don't really have predictive abilities, right? We can't really say much about the ensemble mean if that Gaussian gets too expansive. So then we really need to kind of narrow that Gaussian again. At the analysis steps. That's what's happening. Now, the methods to do this is a few well-known, I guess, famous, you could say methods, or I guess they're the most they're the most commonly used nowadays. So you have your ensemble Kalman methods, right? Where the idea is, as I've mentioned before, you have a certain number of ensemble members. You can push them forward using, you push the ensemble mean forward using the dynamics, and then all of the covariance actually, so that that this kind of I guess it's related to that Gaussian that I showed. That's defined by just using this this matrix multiplication of your analysis members, right? Pushing forward in time. Problem here is that you really need to have sampled your space well enough. To get an accurate covariance sample, a forecast covariance here. So now there have also been other methods introduced from the early 2000s onward, which I think are kind of the state of the art, at least here at the BOM that they use, which are the ensemble transform Kalman filters, which help to get a bit more accurate, I guess, a bit more accurate analysis steps. Forecast covariances, and so the general idea is over here on the right. What you're going to do is you forecast your ensemble mean, and then you add on a term which is your Kalman gain multiplied by this kind of difference between your observations and the same observations in your forecast space, right? So you can kind of vary that. And then what the Kalman gain does is it kind of measures your confidence in your model versus your confidence in your observations, right? So if you're not as confident in your model behavior, you're not going to change, you will change your analysis members and you'll go closer to the observations. And if you're not as confident in your observations, then you're going to let the ensemble members kind of do as they like, right? So that's the general idea here. I don't really want to get too much into the details. I can answer more questions later, but I recognize that I have a lot of information in this talk. So, and also I know that there are some members of that are watching right now that know a lot more about the ensemble data assimilation methods than I do, so they can probably also answer questions. All right, so that's the general idea. You've got this Kalman gain, and it balances your confidence in models versus the confidence in observations. Cool. Okay, so a little bit of background in terms of data assimilation in the unstable subspace. So I was not the first person to come up with this, right? These were ideas that were thrown around since the early 2000s. And the idea came from this kind of thought here from Trevisan and Oboldi, which is that the analysis increment, so that is that Kalman gain term, I guess, that increment should lie in your unstable and neutral subspaces of the model. Right? So in your unstable directions, so your growing directions, or your neutral directions, so the ones just following the flow. That's where we want our increment to lie. And that, in that sense, it's retaining the spatial structure of your dominant instabilities, right? Rather than projecting onto a stable subspace where then you won't catch your instabilities. So in linear systems, this was looked at, and it was noted that the collapse, so that there's a collapse of the forecast error covariance matrix, that PF, into the unstable and neutral subspaces, right? So that was well established in the linear systems. And so what has been done more recently, I guess, somewhat recently, is that this has been extended to nonlinear systems. Okay? And in nonlinear systems, it gets a bit more complicated because we have that the unstable and neutral subspace is actually a function of your underlying trajectory, right? We know that our propagator changes as we move along an attractor in a nonlinear system. So it's not globally defined, that unstable and neutral subspace. And additionally, as nonlinearity increases, you can have that the short-term dynamics will cause your stable modes to experience significant linear growth, right? So that impacts our error growth in our ensemble data assimilation overall, right? So even if the stable modes are also growing, well, that needs to be taken into consideration as well. So in terms of, I guess, empirically, the ensemble Kalman filtering methods have been shown to best capture that unstable error growth in nonlinear systems. However, there's a caveat there. You'll notice that this came a lot earlier than the others. This is when you have a fully sampled system, right? A properly fully sampled, you've fully sampled your subspace, your underlying subspace. So the question is, how do we ensure that we are fully sampling our underlying unstable and neutral subspace? Right? So an idea that we had was in utilizing these things called covariant Lyapunov vectors. So these are related all the way back to Ocelot splitting back in, I think it's the 1960s. I've put the reference down there somewhere. Oh no, that's a more recent one. But so basically what they do, so the covariant Lyapunov vectors, it's related to a tangent space decomposition of your dynamics. And so locally in, I guess, space and in your base space, which can also be in time, they're going to give your expanding or contracting direction. So they correspond to your asymptotic directions, but locally the directions can change, right? And then these vectors also quantify the degree of hyperbolicity at a certain area in base space along your attractor. And then they also allow you, it provides this hierarchical decomposition of chaos, right? From highest growing expanding modes to your most contracting modes. Okay, and this is all related, so through Ocelot's multiplicative ergodic theorem, that's where you get out these lovely Lyapunov exponents that maybe we're all a bit more familiar with and we've heard of, right? So we can see that our ith Lyapunov exponent is related to the asymptotic growth or decay rate in that ith subspace. Okay, so your first Lyapunov exponent will be related to your asymptotic first subspace, right? And then this is all dependent on matrix co-cycle dynamics here. Okay, so for an ODE system, we know that that's just defined by like the exponential mapping of your Jacobian system forward in time. And yeah, as I said, your base space can be your initial conditions based on time. There's many different ways that you can define, your matrix co-cycle. So that's just a bit of theoretical background as to the vectors that we're looking at. So now what are we trying to do with these vectors though? So our idea was, well, we can actually project our ensemble anomalies that we're working with during our DA onto a subset of our covariant Lyapunov vectors, which span that local unstable and neutral subspace. And in this sense, local, I'm saying with respect to time, because we're going along in time, and we're going to do our data assimilation at points in time. So we're going to say at a certain point in time, what are the important, I guess, directions, and so those unstable and neutral subspaces that we need to be actually capturing. So we've done a little, I guess, projection here, a redefinition of our analysis and our anomalies and our forecast error covariance matrix, and then that translates into our Kalman gain calculation, right? Which is how much we trust our model versus our observations. And we just calculate the CLVs using the ensemble mean trajectory over a given window, and we use some algorithms I've listed here from Gary Froyland's work in 2013. And then what we say with the number of CLVs that we're going to use at each analysis step, we're going to determine by calculating a pseudo dimension measure from the FTLE, so finite time Lyapunov exponent. So we're not actually going to take our tau to infinity. we're going to choose some tau, some window, and we're going to calculate our finite time, the Lyapunov exponents, and use them to calculate the dimension. Okay, this will come up in throughout my talk, so I'll use these ideas later as well. So good to get some, keep that in your mind, I guess.
Can I just ask a quick question, Courtney?
Of course.
So are you calculating your covariant Lyapunov vectors from the mean trajectory of the ensemble, or for each ensemble? I mean, it's each ensemble member.
In this case, we've used the mean. We have used that mean ensemble member, and so the idea being that the mean itself will give us the best idea of where we are along the attractor, and then we're going to then project the anomalies. So the anomalies are already sitting there, and then we project those anomalies accordingly where they should be, right? So the idea is if they've gone off maybe into the stable subspace that we're not interested in, we can project them closer to the unstable, right? So that's theoretically what we hope is happening in the background. And we got some evidence that, maybe it is. Okay, so thanks. And anybody can interrupt me with questions at any time, please. So what we did is we chose this kind of paradigm example of chaotic multi-scale behavior, right? It's still very simple in the terms of, the data analysis that we're interested in doing, but it still is complicated enough that it can get us an idea of how these ideas might translate when we do start adding in more and more variables. And so here we have this coupled Lorenz system. I'm sure you all have seen the typical Lorenz system, which is your 3 variable X, Y, Z butterfly, kind of looks the most like this first attractor here, okay? So that's kind of modeled almost the same way in the extratropical system. We've got an extratropical system. That's then coupled to the tropical system. So this is some kind of atmosphere-ocean interaction in the tropics. And that's also Lorenz-like, but it's coupled then to a Lorenz-like ocean attractor, where you can see the ocean attractor has a time scale, so it's acting 10 times as slow as the 2 atmospheric subsystems, right? And then we see that we have various coupling strengths here, right? So our coupling to our extratropical system is quite weak, whereas the coupling between the tropical atmosphere and the ocean, we're saying, is quite strong. And I think this was originally used in the paper in 2004 to look at, well, they discussed El Nino type excursions, right? So the idea being that these big excursions away from the mean in the ocean were some indication of an El Nino event, right? Or an ENSO event. And so we're not really going to think about all of that, but so there was some kind of confidence that it, this model well represents that interaction between the tropics and the ocean. And then we have that other extratropical forcing as well, or coupling as well. Okay, so we're going to pretend this is our Earth system that we're looking at. Now, if we want to consider the asymptotic dynamical behavior, we can calculate these Lyapunov exponents in asymptotic time, basically, and we see that eventually they converge out to very nice values, where we have a large gap, a spectral gap here, right? So what this is saying is, well, our dominant space kind of involves these 7, these 7 Lyapunov exponents here, and then we jump down to very, very stable modes. So we already have some idea that there are probably unnecessary, I guess, directions to be considering if we want to be looking at the unstable and neutral subspace, right? And then we're going to be using this dimension that's called the Kaplan-York dimension, which is defined here. This is a typical one of the typical dimensions used to characterize chaotic attractors. And the Kaplan-York dimension of this particular attractor is nearly 6, right? So 6-dimensional, so 5.9 and so on. So we're going to say it's about a 6-dimensional attractor. Okay, so that's something to keep in mind when we do our different experiments. That's the wrong way. Here we go. So now we're thinking about our local finite time behavior, okay? That was our asymptotic behavior, but we said that when we're doing our data analysis, we actually are going to calculate the dimension at a particular time along our trajectory, and then we are going to choose our ensemble members from that. And so if we compute our local dimension just along the attractor, this is just an example case, we see that when choosing a window of tau equal to 4, so this is kind of on the longer end of things, so maybe like a medium range prediction, we see that it doesn't really tell us much in the there's no structure really going on in the extratropical system, but in the tropical and the ocean there is. And in particular, it really kind of follows these ocean dynamics where we're seeing that, lower dimensions seem to correspond to these like inner loops and the, transitions over to this middle area of the attractor. And then the higher dimensions are when you're on these kind of like more outward excursions, right? So that was just an interesting side thing, but we do see that this changes quite a bit. It changes from about dimension 3 all the way up to dimension 7 throughout the attractor. So what have we done next? So now we've actually tested this on our DA systems. Okay, so I'm just going to give it. We've done a lot of different experiments here, but I'm just going to give a general overview and maybe one or two results, and then kind of point you to more results if you want to look at them. So we've constructed our observations by having a control run. Okay, so we've used some control run, and then we are selecting out of that some subset of variables. Okay, so we've done a few different examples here. One is where we take the benchmark we take one variable from each domain, each subdomain. And then we have like our atmospheric one where we only take a few observations from our atmospheric subsystems. And then we have our what we call the ENSO observations. We're looking at the tropical atmosphere and tropical ocean. And then we look at just our extratropical attractor. Okay, that's in purple because those are the results that I've showed on the side. Okay, so then our assumption is that we take our observations to be the control run value, y bar, plus some perturbation, which is related to our observational error. And then we do this at every 0.08 time step intervals, right? And we have to exclude some model spin up. Okay, so what you see on the right are just where we've taken our observations, the circles here. The red circles are all our little observation points, and we've only observed the extratropical attractor. So that's why I've only put the circles there. And we see that our forecast actually tracks the extratropical system really, really well. But as you might imagine, it struggles a bit more in the tropical system, and it struggles even more in the ocean system. And this is particularly because it's not strongly coupled. Remember, we said that this was a weakly coupled system. So these observations are not giving us enough information necessarily about the tropical system and the ocean system. So we explored in the paper that I'll show at the end of this bit, we explored ways that we can overcome this anyway, including using the various dynamical methods. But this was just a nice, I think, example to show where DA doesn't always work very nicely, right? The other ones work nice, yeah.
Can I just clarify? So by forecast, you mean you take the analysis as your initial condition and you forecast for one time step or for one time analysis window?
For one analysis window, yes.
Okay,
correct.
Thanks.
Yes.
Yep.
Exactly, and yeah, and you can see, I think all of the these are all the various ensemble members are lightly colored in the back. I didn't notice that, so you get a lot more divergence in these areas where it looks a little bit messy and everything, and so that's where we're really not constraining our model well enough, right, with those observations. Yeah, I definitely wanted to show a case where it doesn't work, because some of my other ones looked really nice and almost too nice, and you're like, oh, this is great. But yeah, so okay, so then looking at the case of where we took the benchmark observations, so this is one from each subsystem. So it's almost like we are like fully sampling, so to say, our system. Not fully and not all 9, but at least we have one from each subsystem. And then we trialed out a few different methods of using our CLVs. So we did it using our 9 CLVs, which is full rank, right? We're a 9-dimensional system, so we projected on our 9 CLVs, not really a difference there. Then we used 5 CLVs because there's been papers in the past that said, oh, you can use your unstable and neutral subspace plus 1, right? Use your unstable and neutral and just add that one stable direction. And then we used 6, which was our global dimension, right? The value of our global dimension. And then we also did the methods where we use this variable throughout the DA, where you're utilizing the local dimension. And the main thing I wanted to focus on here are the values in this RMSE full, so the average RMSE of the whole system, right? We can look at each subsystem individually and how they've tracked. But the interesting thing that we see is compared to all of these methods, the variable CLVs comes closest to the full rank, right? Okay, it's still not perfect, but it's still much better than using the 5 or the 6 in this case. So we haven't lost any information. So this is just calculating our total dimension of our attractor. We really haven't lost any information about our attractor by changing our variable rank each time. And as you can recall, sometimes that variable rank changes quite a bit. So here's an example of that. So this is just a 200 time steps, I think, of our run, and these are the dynamics. And so we've got all of our finite time Lyapunov calculated here. And then we have our Kaplan-York dimension and our entropy here. And then at the very bottom, we have the number of CLVs used. And we can even go all the way down to using no CLVs, basically, and not even projecting at all, or doing basically a one-dimensional, I guess, projection in that case. So you could go all the way down. You can vary between 8 CLVs to 2 CLVs. And this is giving just as good results as our full rank. Right, or closer, better than just saying a blanket 5 or a blanket 6, right? And that's really interesting in the ensemble DA space, because really what that means is you could actually change the number of ensemble members you're using from one analysis to another if you have some information about the underlying dynamics. So if you can somehow get this type of measure out from your system and know that you're in a higher dimensional space, oh, well, then maybe you need to use 8 ensemble members at that point. And then maybe you can actually pull that back to 1 or 2 at another point. It's a very, from a computational expense side of things, it's quite a nice thing to have that variability and not lose too much dynamical information and too much information about the system. And this is just to prove to you that the CLVs are acting in ways that we want them to along this, I guess in this window. We see that the mean values and variance are very close to the asymptotic values, right? So, or at least the asymptotic values fall within the variance and the means are quite close. So we have some confidence that, yeah, our CLVs are behaving in the way that we want them to be. Okay. So I keep going the wrong way with that. So yeah, a bit of summary on that part. So basically what we found was that projecting this forecast error covariance matrix onto the CLVs, it allows for possibly the use of fewer ensemble members and or this improved DA performance when actually using an insufficient number of members. So if you know that you're insufficient, say you can only use 10 ensemble members, and your free variables are in the thousands, then yeah, this might be a good way to ensure that you're projecting into the right space. And then the other thing was that the rank of this covariance matrix is best estimated by that measure of local dimension. And I put this in italics because I didn't really show this, but particularly when some subsystems are completely unobserved. So I would point you to the paper if you want to see some more results based on the different subsystems we chose for our observations. But there still remain some challenges, right? This isn't, it's very nice. We've gotten some very nice results, but some of the issues that we saw were that, well, actually estimating this local subspace in a high dimensional system is not so trivial, right? Just applying, Lyapunov exponent vectors and covariant Lyapunov vectors, not so trivial when you get to a really high dimensional system. It's computationally expensive. What do we do in that space? And we started thinking that, well, some such subspaces can have physical manifestations in terms of your climate teleconnections, right? So that's things like ENSO, NAO, and the Pacific Decadal Oscillation. And this actually transitions quite nicely into the second part of my talk. So part 2. So what do we start thinking?
Can I just,
yes,
before, just ask a question on that?
Yeah.
So I mean, you already mentioned it's computationally expensive, like calculating covariant Lyapunov exponent is not cheap.
Mm-hmm.
Have you tried this as well with just, singular vectors and
so
which would be, I mean, still expensive, but a little cheaper?
So it's interesting you mentioned that. So actually, so the covariant Lyapunov vectors, the method that we use is based upon singular vector calculation, but it uses a mix of them. And that actually ties into the end of the talk, like the very last thing that I have to present for today, because we did look into, so basically, if you look at these CLVs on short time scales, they're just a combination of singular vectors. They're a mixing of these singular vectors,
Yes.
but it's done in an almost intelligent way that you don't even realize you're doing it intelligently, like, right? So, you know, it's kind of based on the methodology, and Jörgen Friedrichsen has published some work recently to show the limiting behavior of these combinations and their relation to finite time normal modes and things like that. So it's yeah, I think it is possible because of the fact that we are still using singular vectors in the calculation, right? You have to use combinations, so it'll still be expensive in that there'll be a few you'll have to do a few things multiple times, I guess. It'll be more clear when I show the algorithm later. Maybe okay. I'll follow that up in, yeah. But it's a good point. And it is something that we are thinking along the lines of, like, how do we actually calculate these efficiently? Okay, so yeah, so then we started thinking, all right, now we're gonna go the opposite way around. We've got all this data, we've got this huge problem. We have no idea what the underlying, we don't necessarily know what the underlying dynamical model is, but we need to try to figure out if there is some lower dimensional space we can be working on, right? What our unstable and neutral subspace might look like, or what even a lower dimensional space looks like. So this made us consider whether or not we can use data-driven methods to empirically identify our climate teleconnections, but then using, so we kind of know that you can do that, but can we use those to create a model that shows meaningful dynamical behavior? So the outline here is, yeah, I mean, I'll just go through a bit of a climate teleconnections overview. I'll introduce the methodology that we use and why we've used that. Then I'll look at a couple examples where we've actually looked at the dynamics using these things that I was just mentioning, Georg, these mixed singular vectors, which are just a even shorter time version of our CLVs, and then compare the singular vectors and mixed singular vectors and what you're losing if you use one and don't use the other, and vice versa. So climate teleconnections, if you're not familiar, so these are these basically anomalies. They're relatively persistent. They typically sit around for a few days to a few weeks at a time, maybe even a few months, and they're influenced by each other over quite large distances, okay, thousands and thousands of kilometers. So ones that NOAA has identified specifically on their website is the Arctic Oscillation, ENSO, our North Atlantic Oscillation, Pacific Decadal, PNA. But additional ones that we've considered and thought about are the Southern Annual Mode, which affects our Southern Hemisphere down here, our PSA, our Indian Ocean Dipole, Madden-Julian Oscillation, and so on. And so the interesting thing about these is, so we often see the pictures of El Nino and maybe the Pacific North American Index, but where these often come from, well, that's the question, is how do you get these pictures? And often it's through things like clustering methods, right? We're trying to cluster data around typical types of data, patterns, all of that kind of thing when you're looking at such a large space. So what we started using was this method called FEMBVAR. Okay, that stands for finite element bounded variation vector autoregressive, and it is a type of clustering method. And I'll walk you through basically from what the idea is here. So I'll start on the right. So at the base of this, the method assumes that you have a certain number of clusters of your data, and they behave like local stationary vector autoregressive models, right? So you're going to a priori define, okay, I think there will be 5 clusters or 6 clusters, and they will all behave like a different VAR model. Okay, and then what you do is you use your finite element discretization to solve this cluster functional, which is basically looking at a distance between your data and the various models that you think that it could fall into. So you kind of have your different cluster models, and you're trying to say the data on a given day, which one is it? Which of those models would it be closest to, right? If we fed it into that model, And then and then that's multiplied by some affiliation, as in like it's, 20% it looks like this cluster and 80% it looks like that cluster, right? So you get some kind of affiliation measure as to how well do your clusters capture that data on that day, for instance. And then finally, this bounded variation is really like a final kind of thing on the top, where we just impose that we don't want too many switches between the models, right? We want to say that there's some average persistence of a state. So we're going to impose that there's a maximum number of transitions between our various cluster states, right? So that's all it really is. And the reason why we chose this one is because there's no assumptions a priori on the underlying distribution of the data, which we know is important for climate, because we understand that climate is non-stationary. It's constantly changing due to external factors and internal dynamics and timescales we haven't considered, all of those things. And on top of that, oh wait, that's what I just said, sorry. The assumption of station, so that's what I was just talking about, the assumption of stationarity of the time series. And then, yeah, the underlying distribution of the data. So the data doesn't have to be, Gaussian distributed or anything like that, right? It's we're accepting that our data can be skewed and it can have, some not nice distributions, right? So the other thing that I really liked about this method was this particular setup here, because this has a nice connection to dynamical behavior. Because you can look at this and you could say, well, really, actually, this acts kind of like a mapping with some noise and some translation, right? It's a mapping of your system state with some noise and some translation. So actually, can we pull out some dynamics from this kind of linear mapping system that comes out of our clustering method? So what did we do here? So we did 2 different studies, and I'll present the results of each of them. And we looked at we wanted to look at atmospheric circulation patterns, right? These are typically hard to, there's not as many nice kind of conceptual models for these. So these are a good example for why we'd want to use data-driven methods to kind of get these low dimensional spaces. And we applied the method on some reanalysis data for, I think, some 30-some years, 40 years. And we had to take the leading 20 principal components to apply this to, because even still, you can't do clustering on such a big array of data. You already have to do a bit of reduction. So I think 20 principal components is like 96% of the variation or more even. So yes, we were confident that we were capturing all the variability we wanted. And then we have these 2 regions, right? So the Atlantic region, where we're really focusing over that Atlantic Ocean, and then the Eurasia region, where we're more focused on the continental behavior of the in the atmosphere. So the optimal model that we found for the Atlantic region was 3 clusters with a memory of 3 days and an average persistence of 5 days, right? And there was a nice correlation of what we identified as our negative NAO phase to what is the observed NAO index. So we're pretty confident that this is capturing at least the days and behavior that we want the NAO to be in its negative state. I think I don't really want to go too much. These are just looking at the affiliations in that given cluster state. That's how we've calculated this along with the NAO index. And so those are our 3 main patterns. I think I will.
So just you probably said that, but I forgot just to clarify. So the number of clusters that you specify that beforehand, right? That's not part of optimization, or? So
we did an optimization. I just left it out because it was a bit. I have a slide at the very end to show, because we did a scan basically over a large array of different number of clusters, number of persistence and memory, and then we looked at I think an RMSE value. I have to pull it up, and then we chose one that sat in that kind of like lowest error value. So we did some kind of like optimization technique in the background for this. I just I maybe I'll show that at the end.
Okay,
if that's okay. So that is something that, so the data basically told us in this case that 3 was pretty much the optimal number of clusters. So And that was really nice too, because they actually corresponded to three states that are already well known in the literature, right? This Atlantic Ridge state, the NAO- state, and the NAO+ state. So these all kind of corresponded very, very nicely to already known atmospheric patterns that are the most common to see over the Atlantic Ocean. If you're not familiar, the NAO is related to where you have large regions of anomalous, basically low and high pressure that have this north-south orientation of the Atlantic. And so one is, low pressure in the north and high pressure in the southern region, and then it's swapped for the negative phase, right? And so what the positive phase is often associated with your enhanced zonal jet. It affects your weather, in that you have mild, wet winters in Europe and the eastern US, and also you have stronger and more frequent storms in those periods. And then in the negative phase, you have things like blocking events, you have your cold and dry winters, and you have less frequent storms. And the major impacts, I guess, are, as I just said, in the weather, but also in the intensity and location of that North Atlantic jet stream, right? And I guess the previous belief was that your NAO- should have enhanced predictability, so your negative NAO, due to the fact that it has persistent blocking events. So the idea was like, okay, well, if it's a block, then that means not much is going on. So you should be able to say, oh, it's, there's not going to be much, growth of anything. It's, it should be predictable for the next few days. But recent studies have actually shown that there is increased finite time instability during blocking events, and that your onset and decay of blocks actually have the greatest instability overall. And so really it's like, well, actually then, maybe they're not the most predictable if that's the case, if there's all this instability associated with them. So now I'd show you how we created our dynamical model, I guess. So basically, now we've put it through our optimization, we've put our method through our optimization system, and we've got now optimal parameters and an affiliation sequence, right, from every day. And so what we've done is we said, well, we're going to assign our system to the max affiliation on each given day. Right, so whatever the max affiliation was, that's the state that we're going to say it's in. And then that we're going to have a switching sequence that basically tells us just which state we're in. And then the dynamics are going to be defined by the VAR models on those given days, right? On the given, for the given affiliation, sorry, for the, oh, lost it. For the, yeah, for the parameters that are related to that particular model on that affiliation sequence. And then we can basically translate this into a nice kind of like, it's like a delayed difference equation almost, really. So this is what I already thought of, because this is how we, solve DDEs. And I was like, oh, this is just looking like what we do for linear DDEs. This is lovely. So we can actually just create a nice big linear propagator for our system. It's only three, well, we only have three kind of time steps here, because we only have 3 days of memory, right? If we had 4 or 5 days of memory, this state space would increase. But we've created this nice thing here, that we basically have a linear propagator on our states. So we have some state space of dimension 60. Seems quite large, but we can still work with it. And then we're going to use the same algorithm as before to calculate our CLVs. And now we're also going to identify these things called mixed singular vectors, which are basically CLVs that just haven't really converged yet. So it's using the same method, but we haven't gotten conversion. And the idea is, can these MSVs or CLVs give us insight on model transitions? What we do is we vary that window which we're calculating the MSVs, CLVs, and then we calculate the growth rates. I won't go too much into that because I'm running out of time, but the main difference to look at is wherever our kind of statistics of our daily growth rates align with the asymptotic behavior, we're going to call those CLVs, because we know that the averages of finite time growth over many intervals converge to asymptotic Lyapunov exponents. And now where that doesn't happen, we're going to call those MSVs. And we call them MSVs because that's related to the algorithm that I show in the next bit. So just keeping that in mind, so then we use our finite time dimension measure again, as introduced before. And I guess the big thing that we find is our work, and even in this this model that comes out from this data-driven method, it supports that new interpretation regarding the predictability of blocking events. We see that our NAO minus state, our negative NAO state, has the lowest stability. So we have that increased like local instability associated with that blocked states. And then that could be some insight as to why models struggle to capture this onset and decay of blocking events if there is this increased instability. Sorry if I'm going a bit fast, I just talk too much sometimes. So then, yes, then we just looked at the actual propagation patterns as well. And we noticed that the persistent events that we were pulling out, you get that nice NAO-like pattern. But then the transitional events, so where there isn't really, your residencies are quite short, whether you're in one state or another, that's where you get these zonally oriented anomalous pressure gradients, right? And so that's also been thought of these like kind of like waves that come through across the Atlantic. That's been hypothesized as initiators of transitions into different block states and whatnot. So that was nice to actually see that come out as well in those, where it's those short, not very persistent states. And finally, we looked at alignment because that's often an indicator of transition as well. And we did see that our alignment was increasing as you transition from one state to another. You get this kind of jump in alignment. That's all I really want. I think I'll skip this on more of those on alignment. I'll just do a bit of a summary. So I guess a very simple answer to can the simplified models show meaningful dynamical behavior that come from these data-driven methods? Yeah, they're pretty meaningful. I mean, it definitely aligns with what's been found in the literature and in other more theoretical studies. And then I guess the basic thing is that the push forward step that you're using to calculate the MSVs versus CLVs, it really acts like a time filter on your dynamics, right? So if you use a short window, you're really picking up your individual transitions, or one could think of synoptic scale behavior. And then what we found for the longer push forwards, it was really just characterizing the background state, right? So giving you a seasonal to decadal characterization of your dynamics. And that led us into our final follow-on study, which was how do these mixed singular vectors differ from just singular vectors themselves, and what are those implications on medium range forecasting, so things past 10 days, maybe 14 days. And that was where the Eurasia study came in. And this was kind of prompted because of this idea that MSVs are actually kind of already used in nonlinear and numerical weather prediction, right? So SVs were introduced originally to define your perturbations to your initial state for ensemble forecasting because they project onto your fastest growing singular vectors, right? So you're getting your fastest growing modes to capture those transitions. But then so then they also use the leading singular vectors of the linear perturbations. Sorry. I'm going to skip that one. I'm getting a bit rushed here. Okay, but I guess the important thing to notice is that more recently, ECMWF, so the European Center for Medium Range Weather Forecasting, has incorporated this use of mixed initial and evolved singular vectors, right? So they're trying to capture both the large scale errors associated with small, along with the small scale fast growing ones, okay? So they want to try to capture both. So they have initial, evolved, and they're doing this mixing empirically, right? And so we're like, well, are those just empirical versions of our kind of more, I guess, analytically computed MSVs? So we kind of ran the same thing for the Eurasia region. We also got out 3 states, funny enough, and one looked a lot like, one of our NAO states, which seems to affect the weather over Eurasia a lot as well. I will skip over the details of that because I think this is the more important thing. Comparing our SVDs, MSVs, and CLVs, as Georg was asking before, or kind of touched on before. So your singular value decompositions basically give like instantaneous stretching rates, right? Stretching and contraction rates. Now your mixed singular vectors, because you're actually starting with singular vectors and we're actually evolving them and then taking orthogonal projections of evolved singular vectors to our initial singular vector, like with the propagation of the initial singular vector, we're kind of doing a mixing to calculate our CLVs in long time. We are basically like doing this for longer and longer windows. So when your window is actually finite and small, you're getting this directions of local growth and decay in your tangent space. And the difference, I guess, between SVDs and MSVs are that the MSVs don't have to be orthogonal, which is the same as the empirically calculated mixed singular vectors in ECMWF. And then as you take this to longer time, you get that the asymptotic behavior, right? And so in terms of like the patterns and growth rates, basically your singular vectors consistently show positive growth, right? Even for long time periods that they should be decaying after a long time, but they're consistently showing positive growth as you push them forward. And so that growth is actually pretty unphysical for you have these unphysical small scale patterns that you can see here popping up in your singular vectors over 10-day windows. And then we did look at a study of the Russian heat wave as well, in particular, to see to look at this persistent anomaly over Russia and how that propagated throughout a few days, and compare to, I guess, the singular vectors and the mixed singular vectors and how they capture this. And basically, we find that, again, the singular vectors stay quite positive for a long kind of forward propagation. It takes a lot longer for them to the growth to die down, and that's in all of our vectors, right? Even in our second, third, and fourth vectors. And yeah, so I guess the conclusion we found was that our MSVs are identifying our large scale anomalies, and you're only getting some relative growth, and you're getting just a propagation of those large scale structures, whereas the SVs are just identifying small scale structures, and they're getting unstable growth throughout all 5 days. Right. So that was a bit rushed at the end. I probably put too much in here, as I always do. But so basically, that final study that we did was really to connect these theoretical ideas of short time scale covariant Lyapunov vectors, which we've deemed MSVs, and said that these are actually related to what is optimal for medium range forecasting. Right. And I guess I'll just throw up, since it's, I basically stopped talking now, I'll just throw up the references for those 2 papers. So all the NA results are in there, the first one, and then we've got our results on the singular vectors and medium range weather forecasting in the second publication. And I'll just mention that, there should be more work coming out in this year. There's been a nice data-driven project done by student Gemma Jeffrey, who looked at fitting a recharge oscillator model for ENSO to 96-member reanalysis to get decadal variability in ENSO dynamics. And me and Terry have also been working on a study on these local dynamical measures and connecting them to ensemble prediction. So, all right, I think I definitely should stop now.
Well, thank you very much. That was a great talk. Thanks very much.
Thank you.
Very interesting. Are there questions?
Could I ask you a question?
Yeah.
Hi. Thanks, Courtney. A lot of great stuff in that talk. I was interested in how these singular vectors were calculated, or I guess the CLVs were calculated. You had in an earlier slide this Jacobian of the model.
Yeah. So
I was wondering, I mean, maybe it's somewhat trivial to produce a Jacobian for the Lorentz model or the coupled Lorentz model, but somewhat more difficult for some of these more complicated models.
Yeah, so I guess if that's the thing, if you're using for an ODE, if you don't have an analytical Jacobian, I mean, there are numerical methods for computing Jacobians, which I think they can work just fine in some scenarios if you don't have the exact one. Obviously, that's then another computational expense because you need to be estimating in Jacobian. I think, I think the CLVs are so far a lot of the space that we've worked in are where we had these nice mapping functions, right? I know that people have also worked on this with like Markov models and things like that, where yeah, when you have just a nice linear, obviously a linear propagator already, that's a good thing. But the reason why we bring it up is because linear propagators and tangent linear propagators are commonly used in these kind of high dimensional systems anyway. You know, so it's a space that people are more comfortable thinking about. You know, just taking combinations of your linear propagators. Yeah, I think I guess you just have to estimate the Jacobian. You'd have to use one of these numerical methods for it and see how you go with that for the more complex nonlinear ODEs, and then yeah, and then construct the matrix evolution operator that way. Does that kind of answer your question?
Yeah, I mean, my research is sort of on estimating these linear tangent linear model spaces, but I was wondering if you have the Jacobian for this finite element atmospheric model.
Oh, so this one is very easy. The nice thing about this one is it's already in the linear form. So that's what I'm saying. In this case, it's not, because it's a mapping system in the end. Where did it go? Sorry. Because
right.
You're essentially, yeah, it's a little bit, oh no, I keep going the wrong way. It's a little bit different when you're in the mapping scenario, right? It's because we have this T+1, we've already, you know, done the hard work of, I think the issue with your with the Jacobian aspect, that is to estimate your mapping function forward, right, of your ODE. Gotcha. So I think you're actually doing the hard work already, right? Like estimating the tangent linear model, like that is, once you have that, it's you know, then you can do a matrix co-cycle very easily. You just take combinations of that. So yeah.
Yeah, thanks.
Mm-hmm. Yeah, I guess a follow-up on that follow-up comment would just be, yeah, if you want to get more accurate, I guess, more accurate matrix co-cycle, maybe you use a different underlying model, different assumption, or, you know, it all just depends on your underlying assumption of the model for sure. But at least in the data-driven methods, it's, you know, it's using the data to try to inform the best fit of that linear one. So. I did have here, so this is maybe to follow up on Georg's previous question. Oh gosh, I'm all switched around with my slides here. Here we go, cross-validation, yeah. So we use this cross-validation method to try to choose our optimal model in the end. So we did do a range of different number of clusters. I think we even did 4 and 5 as well at some point, and then they were getting worse and worse. So the results shown here are just for 1, 2, and 3. But yeah, then we did a range of memory, range of days, all taken kind of generally taken from the literature to believe to be the you know, average values. And then, yeah, but you could see here, there isn't really much of a difference between, for instance, this one and using zero persistence, right? They're all kind of very similar. And we looked at, and qualitatively, the dynamical information is the same, right? So if you choose any in that kind of range, qualitatively, they're behaving in the same ways. So that was really nice as well.
I have a question on this FemBVVAR. So I don't know what your range was. I think I went back to 2012 or something, but you know, like the NAL switched kind of from a predominantly, I think, I can't remember, it was negative to positive or the other way around in the 1970s. Have you tried to do that on that sort of longer range? And does your gamma kind of, your affiliation indices, do they kind of capture this, that, you know, on average, like in that period, you just...
So we did not, in this study, we did not do earlier than 79. And I think the change that Terry can probably correct me on this, but I think the change that you're talking about was probably earlier than 79. Yeah. However, Terry did previous studies, and our current PhD student who's on the line as well might do studies in this coming up in that, so Terry's looked at this, the FEMBVVAR, at least in the Southern Hemisphere, moving from, I don't know if it's the 60s upwards, and in the 70s, I think they did see this particular switch in affiliations and basically a die-off, I think. Is that correct, Terry, of one of the...
Yeah, so depending on how you do it, so I'd look, just before I answer that, so whether you do cross-validation or an information theoretic approach to choosing the optimal model, AIC, C, or BIC. For some of these more complex flows, you tend to find classes of optimal models, if you like, where, you know, the ACI-ECA values so close together, it's hard to distinguish. But the general behavior doesn't change that much. But in terms of the, you know, looking at the, if you like, the low frequency variability, there's a couple of ways you can go. One is to use the temporal regularization, so that persistency criteria, to essentially restrict the number, the switching and the persistence of the particular coherent features. And so that in combination, well, that will actually influence the model that you get. The other way to go is that you allow the model to switch at every time step if it wants to, and then you can actually filter the Viterbi path or the model affiliation sequence directly.
So that's getting rid of the BV.
Yeah, that's right. Yeah.
Okay.
So that actually works as well.
Okay, cool.
Yeah.
Thank you. Can I have one more question on the later part? So on the you showed, you know, your singular values, you showed the mixed singular values and the covariant, and the ones that had a non-orthogonal system of modes, you know, that at best is one. Is it correct that one interpretation of this is that if you're non-orthogonal, you can also allow for, you know, a transient growth of stable modes, that is important?
Yeah, well, I think that's the point, right? If it's non-orthogonal, then that is the point, because there is transient growth of stable modes, and you're selecting that window that you're allowing that, right? Because that's the thing. So in long time, you know, in long time behavior, right, that's going to be stable, and you know, it's not going to matter. But you actually do care about those initial. So the thing that has been discussed a lot in the literature is near neutral modes, right? And this idea that the, you know, weakly stable modes actually do experience, you know, a growth, like a local growth, and maybe in dynamics is maybe a little bit different. This is where like the dynamics and predictions, I think, are maybe take a different viewpoint to this, because in the predictive space, you definitely want to capture that, right? Your ensemble members, you need to span that space. You need to span those growing directions, even if just for a short amount of time. Whereas, you know, one might say, oh, in the dynamical system space, one might say, oh, well, that's just transient, and that will, you know, that's not its asymptotic behavior. But I guess that's again, this maybe Terry, you know, he's well established in that prediction space. So.
Yeah, so the thing here is that this particular, you know, the particular FEM VARX model for the NAO, for example, is asymptotically stable, right? But over shorter time periods, it's, you know, it can be locally unstable.
Like
and I mean, Courtney has quite a big section in the talk that she didn't get to on hyperbolicity effectively, right? And so, you know, when you get transitions in and out of these persistent states, then the alignment and the sequence with which the particular MSVs align turns out to be hugely informative of the underlying dynamics.
Yeah, so that was in the watch this space, Terry. I can't give away too much, you know. I might have to give a talk in 6 months' time. So
you sort of, I mean, you talk about SVs and so on, you talk about multi-scale, you know, that you want to capture sort of larger scale and don't want to project onto the small, you know, fast growing modes of that typically associate with, you know, the kind of fast time scales. But have you thought of using BVs, which are, you know, are computationally much cheaper? Although maybe not liked by everyone, but I do like them.
I think we like them. Yeah, we have talked about them. I think this particular exploration was because, yeah, I mean, I think BVs will be slightly different than the mixed singular vectors here. So that's why this was like a nicer connection to the methods, the empirical methods of ECMWF, I think. For the bread vectors, I mean, I don't know. I can't speak as much. I haven't worked with them as much as Terry has, so I can't really speak. I mean, they're mostly, I mean, but they're just like the backwards Lyapunov vectors from what I understand. So you're not taking the forward evolution into account, whereas, you know, with both the ECM, as in well, it depends on which, well, yeah, the bread vectors are, but I think no, you go forward, but then you're looking at the backwards behavior. Is that correct? Like the backwards expansion. Whereas in the mixed singular vector space, I'm pretty sure you're evolving forward, and then you're oh, sorry, now I'm just
But you don't need to
rambling.
linearize. I mean, for their computation is very much cheaper, right? You don't need to linearize. You take the full model and then just look at, you know, the direction of growth after they kind of have a threshold. But I thought
but
forward in time, but
I think that would still be dominated by the leading, like by the fastest growing mode in the end, though. So I think that's the issue there, is that you still are like your length of how far you can go with that before you lose predictive ability is still limited by that window of your fastest growing mode timescale. No,
because the initial perturbation is, you know, away, like a certain distance away, so that eliminates the kind of fast but saturate, you know, then eventually saturating modes.
Yeah, okay.
So that's the idea of Karnai and et al. I think perfect.
The choice of the initial amplitude is essentially determines the structure that you're going to project onto, you know, given your choice of window. But there is some connection between BLVs and BVs.
Yeah, it's a good idea though, because it is, I mean, as you say, you don't need to linearize, and if that's the case, and if you have your model, I mean, yeah, I mean, I would imagine that, you know, some of these ideas can still translate, you know, to the space where if you're deciding to use BVs. I guess the issue is not issue, but maybe the concern would be in an asymptotic value kind of forwards and backwards, and can you, because the nice thing about the MSVs and the CLVs, as I said, where, you know, Jorgen's done this work to kind of show the convergence forwards and backwards to these other dynamical objects, I guess it's, you know, where do bread vectors go in infinite time, right? It's the so then can we actually, you know, are they actually covering the dynamical, you know, or the dimension, right, the underlying like subspace that we're looking for? That would be my question, which is an interesting one. I haven't looked into it, so it could be a good thing to study.
I mean, unless you do something clever, your BVs will just collapse onto the leading Lyapunov vector, right? Given enough time. So
given enough time, so that's, yeah, I guess that's that would be the interesting thing to look at. What is the trade-off, right? Like how much, what is the farthest window that you could go using them to where you've lost then your kind of information? Yeah, it's a thought there.
So part of the motivation here too, and in Courtney's paper shows, is that, you know, the empirical approach taken by ECMWF, it can basically be replaced by just using the tools for generating covariant Lyapunov vectors. You know, so by construction and your choice of co-cycle length, right? You can select the appropriate persistent structures without having to do, you know, any empirical mixing of initial and evolved SVs, which is kind of a nice result, I think.
Yeah, that is nice. But it would come at a cost, obviously. I mean, if you did it.
But I think they're already, but if you're using these, you know, the singular vectors that already exist, and then you know, you're using the algorithm, for instance, provided by Mary that does this kind of projection. In the end, because I guess there would be a cost to the empirical method as well, because I think they have to use like many different like they have to, I forget exactly how it's done, but they do different realizations, I think, anyway, initially, and then they choose based on, you know, certain characteristics which ones they're going to mix, and then I think the actual empirical nature of it might take time as well. So whereas this one's a little bit more methodological. Is that it's more like, you know, it's scripted out, like, okay, you just, you know, at least if you run it one day, it'll be done when you need it, and you don't have to question it and go back and do it again necessarily. Hopefully, we don't know. nothing went wrong. But
All right.
yeah.
Well, thank you so much, Courtney, for a
Yeah,
great talk
thanks.
and a very interesting discussion. And
Yeah.
thank you very
Thank you
much.
for having me. I appreciate it. And I'm looking forward to next month's as well, because I hear that's my PhD buddies. Hey, we had the same supervisor, ironically.